Alrighty then, next video, woohoo! We are going to be picking up where we left off, starting with question number 14. So list all the possible signs of a chemical reaction. What comes to mind when you think of a chemical reaction? What are some of the things you guys think of? Dun, dun, fire. Okay, so fire in and of itself is an excellent example. So temperature change is one of the signs of a chemical reaction, so either in or out. But let's have a quick discussion about the two different types, main types. So if my reactants start with this much energy, and then all of a sudden we do one of these things, and then these are your products down here. Do the products have more or less energy than what you started with? If this is like an energy profile, and we'll say this is energy over here, did energy increase or decrease in that reaction? Yeah, it looks like it decreased. So you can't have destruction of energy. Okay, you cannot. I understand that the products have less energy than the reactants did, but where did that energy go? Just disappear? No, it can't do that. So it went out. Okay, if the energy goes out and you have your hands next to that reaction, how is that going to feel on your hands? It's going to feel warm. And anytime you have that kind of situation where the reactants had more energy than the products, that energy is going to go out of the system, and we call that, if energy goes out, what is that called? Yeah, exothermic. An exothermic reaction will feel hot because heat is being released. Now, what if I have the reverse energy profile? So hold on, here's energy coming up here. Let's say the products kind of start kind of low, have a low, oh, I'm sorry, reactants, I mean. Let's start with the reactants having low amount of energy, and then all of a sudden, now they have a much higher amount of energy when they get to their products. How can this ever happen? What would have to happen? Well, the reactants have to gain energy, right? Where are they going to get that energy from? Energy can't be created nor destroyed, so where are they going to get that energy from? Well, the outside, the environment. So if you have your hand, and your hand is nice and warm, and you put it up to this type of reaction, it's going to suck the heat out of your hand. All right? It's going to grab heat from the environment, and if your hand is sitting there, your hand is your environment. So it's going to suck in the heat. The heat has to come in, so that means energy is going into the system this time. What do we call that if the energy goes in? Endothermic. Okay. So this question right here is on your final. And I realize that maybe this wasn't necessarily on your study guide, so I'm so glad we're talking about it now. These two energy profiles, pictures, are on your final. Okay? All right, so temperature is a sign of a chemical reaction, temperature change either up or down. Let's go back to the fire, though. You want to know another sign? Light being emitted. What could it be another possible sign? Let's pretend like we're at a fireworks show. Yeah, I know, we're talking about combustion here, so keep going. You've been to a fireworks display, correct? What happened? Explosions. Yeah, you can hear them. So sound, production of sound is another sign of a chemical reaction. Now let's get a little bit more specific now. Do you guys remember that beautiful lab where you mix these two clear substances and all of a sudden it got kind of cloudy? Yeah, what is that called again when you get that cloudy thing? There's a word for it. Precipitate. It's the solid, insoluble product. So formation of a precipitate is also a sign of a chemical reaction. And then in that precipitate, remember how they were clear and then it turned white? So color change is obviously a sign of a chemical reaction. Color change. All right, and then there's one more that I'd like you guys to also consider. But you need to be very careful about thinking that boiling or freezing are chemical processes. Is chemical, the identity of the substance has to change. So sometimes, however, when we have a double replacement reaction or even a single replacement reaction, sometimes they produce a gas where a gas wasn't originally there. We call that the evidence of that production of gas or change in state of matter. Sometimes a change in the state of matter can indicate that a chemical reaction has occurred. So I'm going to say here production of gas. Production of gas or state changes. State of matter changes. But be very careful because, you know, like freezing and boiling and things like that, those are physical processes, not chemical. All right, that's a very thorough list. Let's keep going. Okay, number 15. What are the products of a typical combustion reaction? What are the two products, guys? Water and CO2. There you go. Let's keep going. Number 16. Write the net ionic equation for the following and identify the spectator ions. So looking at 16 part A, it starts like this. AgNO3, got some aqueous stuff. NaCl, that's aqueous. And then on the product side, it looks like it is. AgCl, that's a solid. And then NaNO3, and that is aqueous. All right, so we're going to kind of review, obviously, that's the point of this. So I apologize if it seems like I'm going slow, but this is a review process, so enjoy. All right, anything that's labeled aqueous, we are going to separate or ionize. All right, so silver nitrate, that's what this is. So I'm going to separate the silver ion from the nitrate ion. So I'm going to start off with the Ag. So Ag, when you get ions, you have to show two things in the net ionic equation. You have to show its charge, and you have to show its like solubility, like solid, liquid, gas, aqueous. Okay, so silver is a cation, and you can check his charge. He's +1, and he came from an aqueous substance, so I'm labeling him as aqueous. Aqueous means able to dissolve. The next ion that you see here is the nitrate. Nitrate is polyatomic, so I'm going to keep the NO3 together. There he is. That's nitrate. You can look up its formula. That's what he is. And then you have to make sure that you're indicating charge. So I'm going to go -1 and label him as aqueous. Na, sodium, +1, aqueous. Chlorine, -1, aqueous. All right, on the product side, you have this solid substance. Solids are not allowed to be split. In fact, the only things that should be split and have charges on them are substances that you originally labeled as aqueous. So if this guy's just sitting there as a solid, you don't split him, you don't show any charges, you leave him alone. He's your precipitate. So I'm going to go AgCl, I'm leaving him alone, labeling him as a solid S. All right, on the product side though, we also have the sodium nitrate, so I'm going to pop him out. There's sodium. And nitrate. Nitrate's polyatomic, NO3. Get his charge, get his aqueous. All right, so here is what we like to call your total ionic equation with everything written out. But in order to get the net, you have to get rid of something called spectator ions. Spectator ions are aqueous on both sides. So what stayed aqueous on both sides of the reactants and product side? Looks like the Na and the NO3. So let's come to the reactants and get rid of the Na and the NO3. What's left, after you cross those off, that's your net ionic equation. All right, let's keep going. So part B, starting with the K2SO4, aqueous, and the lead, PbNO3-2, lead nitrate. And this will make some KNO3. This dude's aqueous. And the PbSO4. PbSO4. Oh, by the way, it didn't label solubility. My bad. I was supposed to review that. So the products don't have the label of solid, liquid, aqueous, or anything like that. So you would have to go to your solubility rules and double check everything. But if you look at your solubility rules, it says that all nitrates are soluble, 0 exceptions. Moving on, let's talk about this other product, this PbSO4. That is called lead sulfate, and technically we should say lead 2 sulfate because sulfate's -2, and there's only one lead attached, so he has to be +2. So this is lead 2 sulfate, so you'd go to your sulfate rules. Is sulfate on soluble or insoluble side? I can't remember. I could pull it up and look, but there's so many of you guys here. Anna? Yeah. Soluble? They're soluble unless they have silver, mercury, or lead. Is that correct? Oh, calcium and barium. All right, cool. So silver, mercury, lead, calcium, barium. Do I have that right? And strontium? All right, cool. So you have a metal on here that is an exception to the sulfate rule. Sulfates are supposed to be soluble unless they have one of those unique metals on there. This is a unique metal. So instead of labeling this guy as a soluble, I'm going to come over here and label him as insoluble. What symbol do I put there? He's insoluble. S. Good job. All right, there's just one more problem with this particular reaction. The previous one was nice and balanced for you. This one is not. Can you tell? Look on the reactant side. How many Ks? Yeah, you got 2 there. Look on your product side. Here's K. See how there's only 1 sitting right there? So what do I got to do this dude? I'm going to place a 2. That'll give me 2 potassiums. It'll also give me 2 nitrates, but that's what you need because you look on the reactant side, you see the 2 nitrates. All right, everything's all labeled, everything's all balanced. We are ready to rock. Okay, so starting on the reactant side, you got some potassium sulfate. That's what this is. Now, the reason why there's 2 potassiums sitting on this guy is because potassium has a positive 1 charge. How do you show more than 1 ion in your net ionic equation? How do you do that? Now you put that big number in the front. It's called a coefficient. So I have to have a big number 2 in the front. This is potassium. Get his charge and label him aqueous. So that's 2 potassiums. Don't say K2, say 2K. All right. Sulfate. Sulfate is polyatomic. Got to keep the SO4 together. You can look up sulfate, to double check your formulas, what needs to stay together. This has a negative 2 charge, and he is aqueous as well. Let's check this lead. If he has 2 nitrates on there, that must mean that lead has a positive 2 because, nitrate is negative 1. All right, now nitrate is NO3. That is its formula. How many nitrates are in lead nitrate, or lead 2 nitrate if you want to say it right? There's 2 nitrates, so that means that I have to go like this. That's another case in which you have to, use a coefficient. All right, keep going. The product side, this dude's aqueous, this potassium nitrate, so keep it coming. Remember, you got 2 potassiums, so don't forget that coefficient. You have 2 nitrates. Again, don't forget the coefficient. All right, that last product, that lead 2 sulfate, that is a solid. Remember, don't split apart your solids. And no charges on solids, liquids, or gases. All right, get rid of your spectator ions, the stuff that stayed aqueous on both sides. That was your potassium and your nitrate. So get rid of them, and then you're done. All right, let's move on. Number 17. Okay, number 17 had a typo on there, so make sure you found it. Everything that says K, basically you're going to change to say Ag. All right, so the reaction now looks like this. MgSO4 plus AgNO3. This guy's aqueous, this guy's aqueous. Okay. MgNO32 plus Ag2SO4. And this dude is your solid. There. All right, that's looking a little better. Now, first things first, you can't do any stoichiometry unless the reaction is balanced. Okay, so on the product side, you'll notice you have 2 nitrates and you also have 2 silvers, the Ag. So to fix that, come over here. Here's where your Ag and your nitrate is. So I need 2 of those, so I'm just going to stick a 2 right there. All right, now it's ready to go. All right, let's start with part A. If I produce 6.5 moles of MgNO32, so come over here. This is part A. If I make 6.5 moles of this, and it says how many moles of K2SO4 are also produced, and remember that's now AgSO4, so. All right, so moles. Oh, sorry, formula units, sorry. Formula units, question mark. Wait, no, it is moles. Dang it. Sorry. Erase. I kind of like to, over the top of a balanced reaction, write what I've got and write what they're asking me for. So sorry, this one is, again, moles. Okay. This one you can actually do without any math, in my opinion. You should just be able to look at this and say, okay, what's the ratio between the magnesium nitrate and the silver sulfate? Guys, what's the ratio between those two guys? It is 1 to 1. You see how in the front they don't have anything? So if you made 6.5 moles of magnesium nitrate, how many moles of silver sulfate did you also make? Same number, 6.5. All right, answered, done, no math. go to part B. All right, if I have 14.6 grams of AgNO3, how many formula units of magnesium sulfate do I need? So you're starting with, again, 14.6 grams of AgNO3. So you're starting with 14.6 grams of this. And they want to know how many formula units of magnesium sulfate. So I'm not cursing at you, formula units. Okay, those are actual ionic compounds. So you're starting here and you're going there. All right, so this is some stoichiometry. Starting with the 14.6 grams of AgNO3. All right, so in this particular problem, you're starting with the mass of A, which is up here at the top of the screen, right here. Starting with mass of A. So we're going to change mass to moles. Then we'll look at that balanced reaction so that we can look at a mole-mole ratio. And then at the very end, they want us to end with formula units. And formula units are basically ionic compounds. And that is a type of particle. So they want you to use Avogadro's number at the very end of that problem. It's always good to kind of look at these things and just kind of review. All right, so starting with mass, ending with formula units, make sure you hit that mole-mole ratio from the balanced reaction. All right, let's begin. So I start with mass. Got to get rid of that. So the silver is, let's see, 107.9. 107.9. And let's see, nitrogen is 14 and oxygen is 16 each. I have a molar mass of 169.9. Anybody confirm? Cool, thanks. So where do I put 169.9 grams? You've got grams. Remember, you have to cross cancel, so grams have to go down here. 169.9 grams, that's equivalent to 1 mole of AgNO3. All right, now that I've converted my mass to moles, we now need to hit, if you look back again, you need to hit that mole-mole ratio. This is the heart of your stoichiometry problem. So now come and look at your balanced reaction. For every 2 moles of AgNO3, there's 1 mole of magnesium sulfate. Cross cancel with the same substance. So if this is silver nitrate on the top, you have to have silver nitrate on the bottom. And I'm looking at that balanced reaction, so there should be 2 moles of silver nitrate for every 1 mole of magnesium sulfate. Okay. And this will cross-cancel moles AgNO3. All right, we have to end with formula units. So formula units is a type of particle, and how many particles are in a mole? Because we need to get rid of moles here. So if I have 1 mole of MgSO4, how many formula units will that be? Yeah, 6.02 times 10 to the 23rd formula units. There we go. And that will cross-cancel your moles. All right, start with that number at the top. That means I'm just going to punch in 14.6. I will divide by 169.9 because it's on the bottom. I will divide by 2 because that's on the bottom. And then times 6.02 E23. Boop. Okay, on the calculator, this is what I get. 2.5865, and it keeps going, times 10 to the 22nd. All right, so sig figs, mole ratios don't count. The numbers 1 don't count. Let's see, so this guy's got 3. We have 4 on that molar mass and 3 again. So let's round to 3. 1, 2, 3. Does the 8 need rounding? Yeah. So 2.59 times 10 to the 22nd. And what you should be saying is formula units of magnesium sulfate. And that would be your final answer for B. Okay, so let's continue on to C. All right, if I could drop 6, and I hate this word molecules, that should actually say formula units. If I could drop 6 formula units of magnesium sulfate, so look up here, 6 formula units of magnesium sulfate in a bunch of, again, that's silver nitrate, how many molecules, and I shouldn't say molecules, but formula units, how many formula units, and that'll be silver sulfate, how many formula units will you have? All right, so we're going from magnesium sulfate to silver sulfate. And technically what they started you with is not very many formula units. It's like only 6 formula units, 6 compounds basically, 6 ionic compounds. And you can actually do this in your head, but for those of you who maybe you're thinking funny, I'm going to show you what this will look like. So 6 formula units of MgSO4. Now I'm actually going to go ahead and do like a full stoichiometry problem and just show you that. But hey guys, what is the mole ratio between MgSO4 and silver sulfate? 1 to 1. So if I start with 6 compounds of magnesium sulfate, I should be able to make 6 compounds of silver sulfate. The answer is 6 formula units of silver sulfate, because it's a 1-to-1 ratio. But many people, when they see formula units, they totally freak out. And so if you come back to this image, basically what you could technically be doing is starting with particles of A, dividing by Avogadro's number, doing a mole ratio, and then ending with Avogadro's number at the end. Technically, that's what it is. So if I wanted to, I could actually do a full stoichiometry problem here, but let me show you what it would look like. Since you have formula units, there's 6.02 times 10 to the 23rd formula units in 1 mole of magnesium sulfate. Now what you would do is you would look at the balance reaction between magnesium sulfate and silver sulfate, and it's a 1-to-1. So for every 1 mole of MgSO4, there will be 1 mole of Ag2SO4. And then from here, you're trying to get back to formula units, so what you would have to do is multiply by Avogadro's number at the end. So for every 1 mole of Ag2SO4, there would be 6.02 times 10 to the 23rd formula units. So here's the fun part, guys. In long time ago, when we were learning about cross-canceling, do you see this big fat number on the bottom, and then do you see it here on the top? Don't those technically cross-cancel? The actual number cancels? All right, the answer is 6. So 6 formula units, don't say molecules, okay? 6 formula units of Ag2SO4 is your final answer for part C. All right, let's go to part D. Okay, if I have 7.50 grams, again, of AgNO3 and an excess of magnesium sulfate, it means magnesium sulfate just won't run out on you. That's what excess means. It's not part of the problem, by the way. And I produce, so hold on, let me just kind of erase and organize the information here. Okay, so they are giving you 7.50 grams of silver nitrate. So come to silver nitrate, and they are giving you 7.50 grams of this. Excess of magnesium sulfate, that just means it's not going to run out in you. And you produce 3.20 grams, again, change the K, so we're coming here, 3.20 grams of this stuff. What is my percent yield? All right, so we're starting on silver nitrate, and we're trying to go to silver sulfate. And this time you're starting with mass, and then they tell you what you actually produce. It's kind of like an experimental amount that they actually produce. So here we go. Traditional stoichiometry problem. Starting with mass, you need to hit the mole ratio and then end with mass. All right, silver nitrate, luckily you've already done the molar mass of silver nitrate. It's 169.9, so we can just plug that in. 169.9 grams per 1 mole AgNO3. Okay, so we're starting with the AgNO3. We're trying to go to silver sulfate. The mole ratio between those two is 2 to 1. So be very careful. Who gets the 2? Silver nitrate. So you have silver nitrate here. Make sure on the bottom that you're saying 2 moles of silver nitrate for every 1 mole of the silver sulfate. Okay. So now that we know that we've made, that we're here on silver sulfate, we're going to figure out how much we were supposed to make. So let's end with the molar mass of silver sulfate. cross-canceling, right? Grams, grams, moles, moles. Hey, we got moles, so we're doing molar mass. 1 mole of Ag2SO4. Let's get that figured out. 7.9 times 2. 32.1 is sulfur. 16 times 4 is oxygen. I got 311.9. Can anybody confirm that for me? Thank you. 311.9 grams. All right, let's solve. 7.5 divided by 169.9 divided by 2 times 311.9. I get 6.88419, and it continues. So how many sig figs here? This guy's got 3. This has 4. That doesn't count. This has 4. So we should probably do 3. 1, 2, 3. Do I need around that last 8? No. So 6.88 grams. Now look at what we did in order to figure this out. This math means that you have calculated how much you were supposed to get. That is sometimes called your theoretical yield, how much you were supposed to get. Now in part D, it says, and I produce 3.20 grams. That right there is what you actually got. This right here is what you were supposed to get, your theoretical yield. So this is an important formula. You will be using this several times on your test. Okay, I've seen 2, maybe 3 questions so far. So percent yield is just what you got, actual, over what you should have got, theoretical, and then make sure you just multiply by 100. Great stuff to put onto your formula card, onto your little note card. You get to have a note card. That would be great to put on there. All right, so the actual is going to be 3.20 grams. The theoretical is going to be 6.88 grams, and then times by 100. Let's see what you get. I got, keeping with the 3 sig figs, I got 46.5%. Final answer. Making sense so far? All right, so that was D. Let's keep going. Part E. Lots of information here, okay? This is a big one. So coming back on this balanced reaction that's been obliterated. Hold on, I'm going to erase all of that junk. Okay, so we're on part E. Let's take a look at what they gave you. They gave you 5.63 grams of this one. 5.63 grams. They gave you 5.63 grams of the other one. 5.63 grams. And they say, which one is my limiting reagent? What's my theoretical yield of, again, that's AgSO4, so they want to go here, theoretical yield. And then how much excess is left over, and then if I actually produce 1.35 grams, okay, so in the lab, so this is what we call our actual, they want to know, what is your percent yield? Okay, so guys, if you have 2 quantities, what do you have to do with that? 2 problems, and both of these are going to go to the same spot. How do you know which one's the correct answer, or like the amount that you were supposed to make? The lesser amount. Do you remember that? The lesser answer between these 2 is going to be your theoretical yield, the maximum you can make. All right, so here we go. Now that you got a plan, let's do it. Okay, so starting here. Let's start with the 5.63 grams of AgNO3, right, because that's not K, that's Ag. So we'll do one stoichiometry problem here, and then we'll do another one here, 5.63 grams of the MgSO4. Best part about some of this is that you've already done some of the molar masses here, all right? Molar mass of silver nitrate, again, is 169.9. And get that down here. Basically, we're converting all of these to moles so that we can look at the balanced reaction. All right, MgSO4, magnesium is 24.3, S is 32.1, oxygen 16 each. Oops. Times 4. I got 120.4. Can anybody? Yeah? Thank you so much. Okay, so 120.4 grams per 1 mole of the MgSO4. All right, what comes next in both of these problems? What do I have to do here? What's the next step? Mole-to-mole ratio. All right, so let's look at AgNO3. Let's check that one. AgNO3 is 2 to 1. The 2 is in front of the AgNO3, so come down here. The 2 is in front of the AgNO3, so coming down here. Got to make sure I put that 2 right here with the AgNO3. So for every 2 moles of AgNO3, what are we going to again? What are we supposed to be going to? Ag2SO4. So we're going to stick that 1 mole of Ag2SO4. Okay. So coming down to this bottom half, the magnesium sulfate. Check magnesium sulfate. Magnesium sulfate doesn't have anything in front of them, so that's a 1 to 1 mole ratio. So let's go ahead and fill that in. For every 1 mole magnesium sulfate, you are going to make 1 mole of silver sulfate. All right, how do I end on both of these? What do I need to end with? Mass, right? Mass of the silver sulfate, and I think we already did that before, so I'm going to come back up here. Molar mass is 311.9. So let's get those in. Again, 311.9 grams is equivalent to 1 mole of this stuff. All right, let's get that in. 311.9. Okay, so you're going to get 2 answers, and we already said this before, but I'm going to say it again. The lesser number is the maximum you can make, your theoretical yield. So I'm doing that top one, 5.63 divided by 169.9 divided by 2 times 311.9. On this one, I'm reducing to 3 sig figs. I got this on my calculator, 5.167. So what should I need to reduce that to? 5.17 grams. Okay, so this one is 5.17. Let's do the bottom one. 5.63 divided by 120.4 times 311.9. This one, also reducing to 3 sig figs, it says 14.58. So what should I reduce that to? 14.6 grams. All right, so which one is the maximum amount that we can make? That's right, the 5.17. So this 5.17 right here, this is the max that we can make. So we call that the theoretical yield. Theoretical yield. That's a maximum that we can make, okay? Now, which reactant, therefore, limited how much we can make? Silver nitrate or magnesium sulfate? Which one limited the max we can make? The silver nitrate. So the silver nitrate ran out and stopped the chemical reaction. It limited how much we can make. Therefore, we're calling this guy your limiting reagent, because he limited how much product we can make. And once he was gone, that's it, the reaction stops. So guys, this magnesium sulfate, we used some of it, but we did not use all of it. Therefore, this guy is in excess. And you guys have a job to do. You have to figure out how much you used so that you can figure out how much is left. We know that we made 5.17 grams of product. We made 5.17 grams of the silver sulfate. The question is, how much magnesium sulfate did it take to make that specific amount? We did not use all of the 5.63 grams of magnesium sulfate, but we did use some of it. So what we're going to do is we're going to work a problem going back to figure out how much we actually used. So I'm going to come back over here, and this time I'm going from silver sulfate to magnesium sulfate just to figure out how much we actually used. All right, lucky duck, you already have all of your molar masses done. So 311.9 grams is equivalent to 1 mole of your silver sulfate. Now remember, we're going from silver sulfate to our excess, magnesium sulfate. So you may want to double check. What's the mole ratio between magnesium sulfate and silver sulfate? Yeah, magnesium sulfate is 1, silver sulfate is also 1. So I'm going to stick in a 1-to-1 mole ratio. Ag2SO4. And I'm going to, again, my excess, MgSO4. Got the molar mass of this guy too. You already did it. And this is 120.4. Now remember, what this is solving for is how much magnesium sulfate you actually used. Not how much is left over, how much you used. So let's grab that 5.17. Let's get going here. Divided by 311.9 times 120.4. And I get 1.995. I should be reducing to 3 sig figs, huh? All right, so what do I do? Because that needs to round up. That rounds up. That's going to make that dude round up. And what is that 1 is that going to turn into? 2, but I'm supposed to have 3 sig figs, so those 9s are going to be converted into 0s. This represents the amount of magnesium sulfate used. Amount MgSO4 used. So how do I get my excess? Well, you originally started the problem with 5.63 grams available to you. You had 5.63 grams MgSO4 available to you. But you only used 2 grams. Subtract. That's going to give you 3.63 grams left over. And there you go. There's only one question that we need to answer at this point. We've got the excess, we figured out the theoretical amount, we know which one's limiting, which one's excess, and how much excess. You just need to do your percent yield. You were supposed to get 5.17 grams. All right, if you go back to the original problem, it says you actually produced only 1.35 grams. Wow, that's pretty lame. So you actually only produced 1.35 grams of this stuff. This is what you were supposed to make, but this is what you actually got. So how do you do your percent yield one more time? It's what you got divided by what you should have got, kind of like on your test. Take your score and divide it by the maximum score you were supposed to get. You were supposed to get 100%. All right, so 1.35 is on the top, 5.17 is on the bottom, times it by 100. And I get 26.1%, 3 sig figs. Percent yield. Woohoo! What number was that? 17. Hallelujah, it's done. All right, that means we're on number 18. Okay, it says for the following single replacement, determine if the following reaction will occur, and if not, say why. But if it does, I want you to give me the net ionic equation, the half reactions, and label those half reactions as either oxidation or reduction. Dun, 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 dun. All right, part A. Part A says you've got magnesium metal in hydrochloric acid. Hydrochloric is HCl, so I'm saving you guys a little time. First of all, will this reaction work, and how do you know? What are you supposed to check on single replacement reactions? Yeah, metal reactivity series. All right, so let's check out this magnesium and see what it says about it. Magnesium is right here, It's in that second box down. It says these metals displace hydrogen from acids. So it's going to kick off the hydrogen in the front, and it's going to be able to produce, when it kicks it off, it's going to be able to produce some hydrogen gas. So we know that one of the products has to be some hydrogen gas. Cool, cool. And it works. This reaction does work. So what's the other product, though? Once the hydrogen gets kicked off, the magnesium and the chlorine are going to come together. Okay? This right here is kind of like your element. So a single replacement reaction, the way it usually works, it kind of looks like this. You have an element, and then you have a compound. And basically, you'll have a totally different element and a totally different compound. So who's this compound that I need to make? Yeah, you see how we have magnesium left and we have chlorine left? We're going to make some magnesium chloride. It's the only 2 elements we haven't used yet. Whenever you make a compound, what did I say is the rule about making a compound? What do you always check? Charges. Magnesium, element 12, positive 2. What about chlorine? Negative 1. So this is positive 2, negative 1. You've got to balance that charge out. Okay? All right. Now, the next step here is labeling solubility or balancing the reaction. whichever you prefer to do first. It doesn't really matter. A lot of people forget what to put when there's an acid, when you have like a hydrogen in the front. Well, hydrogens should be treated as if they were like alkali metals. So if you're ever wondering about the solubility here, if you come in here and you're like, oh my gosh, what's the solubility? I can't find hydrogens. What do we do? Well, hydrogens are like alkali metals, and so if you come over here and you look at chlorine, you know, if we were doing hydrochloric acid, read chlorine, it says all chlorides are soluble except silver, mercury, and lead. Hydrogen should be considered like an alkali metal, so here's the bottom line, guys. All acids should be labeled aqueous because they're like an alkali metal. Anything with an alkali metal in the front is always going to be aqueous. So let's come back over here. This HCl right here, let's label him as AQ. So this dude's aqueous. Come over to magnesium. It's just a strip of magnesium. What do you want to call him? Solid, liquid, gas, or aqueous? He's a solid. He's a metal. All right, so hydrogen is a gas, right? We're cool with that. But what about this compound, magnesium chloride? He is, you know, like ionic. So you may want to go back and check your solubility rules. It did say chlorides are soluble unless they have silver, mercury, or lead on them. So we don't have one of those special metals attached. So this guy's going to be soluble, AQ. All right, now that we have everything labeled up, we can start working on the net ionic equation. Remember, anything that says AQ, you're going to break them up. Anything that says solid, liquid, or gas, leave it alone. Okay, you can only break up stuff that says AQ. So let's do it. This does not say AQ. Leave them alone. But this does. So this is an acid, and acids make hydrogen ions, right? One of the things I forgot to do, and I think you guys can tell now, right? I forgot to balance the reaction. Can you tell though? Look over here. You see how you have two hydrogens and you have two chlorines? Yeah, I'm going to take care of that right now. I just now caught it. Oops. All right, so how many hydrogen ions and how many chloride ions do I have here with the two HCl's? Got two of each, right? That balanced my reaction. So how do I show more than one ion in a net ionic equation? What do I have to stick in the front? Coefficients. So two H pluses, get the charge on there, label him aqueous, and two chlorines, get the charge on there, label him aqueous. But as you move to the product side, that's a gas. Leave him alone. Remember, we're only splitting up stuff that says AQ. Magnesium chloride is AQ, so I'm going to break this guy up too. Magnesium, check his charge. Get aqueous. Chlorine. Hoo-hoo. You see how there's two chlorines? Why don't I say Cl2? Why don't I say Cl2? This is wrong. Why? How can you tell? The chlorine came from an ionic compound. It is not chlorine gas. If it was chlorine gas, you could say Cl2, right? But this is the chloride ion. This is called magnesium chloride because the chlorine turned into an ion. Okay, so this is wrong. Get rid of that little subscript 2. That's bad. This is an ion, and he has a charge, and he is aqueous. All right, what's the next step? Get rid of your spectators. Sound familiar? Spectator ions, stuff that's aqueous on both sides. All right, now we're on to half reactions. So half reactions concentrate on one thing at a time. So let's concentrate on magnesium, and let's see what happened to magnesium. Magnesium started off as a solid, and he turned into an ion with a positive 2 charge. Now let's look at hydrogen. Hydrogen started as an ion, and he turned into a gas. Okay, now comes the hard part, figuring out which one's oxidation and which one is reduction. So let me help you out. Do you guys remember this cool thing? Oil rig. Okay, this stands for oxidation is loss and reduction is gain. So it might be kind of hard at first to kind of figure out which one's which, so I've got some suggestions. All right, but I do have some suggestions on how to get started here. So the first things first, I kind of like looking at the half reactions and figuring out where the charges are located. So solids, liquids, and gases, they don't have any charges. So this magnesium right here has a charge of 0. But you see how this ion sitting here has a +2 charge? So this guy is +2. Do the same thing on the other half reaction. You have 2 +1 ions, so make sure you're paying attention to your coefficients when you're looking at your charges. So this is technically 2 plus, +2. And solids, liquids, and gases, they don't have any charges, so that's 0. Now that I see the charges, it kind of helps me personally, because we're going to do 2 things. We're going to be adding some electrons to the right side. We're going to figure out which side to put the electrons on. And then we're going to figure out which one's oxidation and which one is reduction. So coming down here, just kind of a mental thought process. If you lose electrons, you need to think about which substance likes to gain or lose electrons. Metals. Metals are on the left side of the periodic table. They like to lose electrons. Remember how metals are a bunch of losers. So if metals on the left side of the periodic table, if they lose electrons, do they become positive or negative? You're losing negatively charged stuff. What does that make you? Makes you more positive, right? So this becomes more positively charged. Okay, I'm just kind of putting that as a mental note. But if you gain electrons, you're going to become more what? Yeah, more negatively charged. And this kind of helps me to figure out which one's which. So coming up top, did magnesium become more positive or more negative? He went from 0 to a +2. He became more positively charged. And so I know that that means that this first one has to be oxidation. Now let's look at the second one and make sure that makes sense. You started off with a +2 charge and you became 0. Think of a number line. +2 is up top and you dropped down to 0 charge. You reduced your charge. You started at a +2 and you came down. And by the way, that's how I always remember it. Reduction is reducing your charge. Reduction, reducing, reduction, reducing. So this guy is reduction. Now let's get the darn electrons on the proper side. So remember, what charge are electrons? Negative. And the point is that you need to make these half reactions have the same exact charge on both sides. I don't mean +2, -2. That's equal and opposite. I said same, as in identical. So where should I put the electrons in this first one? Should I put it on the left side or the right side? On the right side. You have a +2. If you put a couple electrons on the right side, if I go like this and add, 2 electrons here, the 2 electrons are negative, right? What's +2 and -2 give you? 0, right? Magnesium 0 on the left. The products are 0 on the right. That's the proper location for your electrons, on the right-hand side of that first one. So come down to the second one. You have a +2 sitting on the reactant side. Let's get a -2 right there, so that these guys right here cancel to give you a 0 as well. Just remember, electrons are negative, and the charges on the half reactions have to be identical on both sides. And always, your electrons will be on opposite sides from oxidation to reduction. They're always equal and opposite. Okay? All right, hope that helped. All right, part B on number 18 is all about magnesium and water. So magnesium and water. Let's see if this is going to work. So come back to that metal reactivity series and let's see what we got. So here's where magnesium is, and it says these metals replace hydrogen from acids, and I made you guys kind of write in a key word, only, from acids only. So yeah, water has hydrogen, but it's not strong enough. So when you stick a strip of metal, magnesium metal, into water, it's not going to be able to displace it. And I can actually tell you from experience that if you stick solid magnesium in water and heat up the water like a lot, that reaction will go very, 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 very slowly. So you can force it. Just saying, it only works with magnesium. I can't remember what the next metal is underneath there. What is that? Aluminum? Yeah, aluminum won't do that. Thank goodness, right? Think about like if you were on anybody on a camp out this last weekend? Yeah. Could you imagine if your aluminum foil actually reacted with all of the juices and stuff that, like, I don't know if you wrap your meat in like aluminum foil and stick it on the grill, or maybe, you know, vegetables or whatever, and you stick that on the grill, right? Could you imagine if your aluminum foil actually reacted with water? That'd be really bad for your health. You'd be like creating like a whole bunch of hydrogen in there. Anyway, I find these things funny. All right, so this is not going to work. So no reaction because magnesium does not react with H2O. It's not reactive enough. Not reactive enough. All right, that's all good. Okay, number 19. Okay, magnesium nitrate and potassium carbonate react together. Write out a balanced reaction. Identify the precipitate. If you need to make 2 grams of precipitate, how much of each reactant would you need? All right, so let's start with those words. Magnesium nitrate. Magnesium is Mg, nitrate is NO3, and you're making a compound, so you got to check your charges. Magnesium is +2, nitrate is -1. All right, so what do we do about this NO3 if we need more than 1? Yeah, parentheses, because it's polyatomic. All right, let's look at what else it's reacting with. Potassium carbonate. Here's potassium, here's carbonate. Check charges. Potassium is +1, carbonate is -2. All right, so we got to go like this. And all it does is tell you that these guys react, and you've got to figure out your products on your own. Okay, what kind of reaction is this? Just looking at that so far. Double replacement, good job. So who is magnesium going to hook up with on the other side? He's going to want a different negative dude, anion. Magnesium's going to want CO3. All right, so Mg, CO3 come together. You can check your charges. Magnesium is +2, carbonate is -2, so that's perfect. Who's the other product? Who's K going to want? Yeah, he's going to want that nitrate. So K and NO3 come together. Check their charges, positive, negative, 1 each, so it's set. All right, the only thing left to do is to label your solubility and balance the reaction. All right, so let's go ahead and try to figure out the solubility first. All nitrates are soluble. I don't know if you guys have memorized that yet, but that is a really nifty rule to just remember. Nitrates are always soluble. So if it's soluble, I'm coming over here, I'm going to label AQ, and there's another nitrate over here, AQ. All right. On carbonate, you can check him. So carbonates say, all carbonates are insoluble except alkali metals. So let's see who we have attached here. You have a potassium carbonate. Potassium is element 19. He's in the first family on the periodic table on the left-hand side. Those are your alkali metals. So he's going to be soluble. But is magnesium an alkali metal? No. He's element 12. He's in the second family. Those are called alkaline earth metals. So guys, he's an exception. He's a special metal. He's no good. Solid. Or he's not an exception, I should say. So he's solid. All right, so let's come into number 19. Let's balance this reaction. Let's see, you have 2 Ks and 2 NO3s on the left-hand side. Did you notice? All right, so let's get 2 Ks and 2 NO3s on the right-hand side. All right, now it's balanced. Okay, now let's read the problem. If you need to make 2 grams of precipitate, who's the precipitate? Yeah, the MgCO3. This is your solid product. If you need to make 2.00 grams of this, the question is asking you, how many grams of each reactant will you need? So you need to go here and here. How many problems should I need? 2. That's right, you have to do 2 setups. One is going to go to the potassium carbonate and the other one to the magnesium nitrate. All right, starting with this. So one problem, and then let's do the other problem. Going to each reactant, okay? All right, let's do some molar mass. Okay, so we converted both of those masses to moles. All right, now, in order to move from one substance to another substance, we have to look at the mole ratio. So the mole ratio all across the board, it looks like they are all covered in ones. I don't see any coefficients in front of any of those except for the KNO3. But that's not part of the problem. So everything is 1 to 1. Let's fill those in. So I've got 1 to 1 mole ratios. On one of them, we're going to go to potassium carbonate, and on the other one, we'll go to magnesium nitrate. So I'm going to convert now to mass at the very end. So notice you're on MgNO3 and K2CO3. So we're going to end these on their molar masses. All right, we got those molar masses. So now all you have to do is just solve both of these, and this will tell you how much of each reactant you need. All right, and I got 3.29 grams of potassium carbonate and 3.52 grams of magnesium nitrate. So we'll go ahead and stop here. All right, so basically I got you guys pretty far along. You're welcome. I got you guys through 19. All right, you guys, obviously we'll keep going as far as we can.